So continuing with the instruction set of the x86 processor, today we will look at operations which are related to stack. At the same time, we will try to understand how the stack works. So the two instructions which are associated with the stack are the push and the pop instructions. This is used for storing or retrieving data from memory. A stack memory is a special kind of memory which has the last in first out policy. That is, the data that is stored last will be the data that is retrieved first. So it is last in first out policy. Generally, memory you access in a random manner, that is why it is random access memory. But once it comes to a stack, there is a certain order in which the data is pushed into the stack, and there is a certain order in which the data is popped out of the stack. So the last data that is stored or pushed into the stack will be the first data that is retrieved or popped from the stack. So it is last in first out. Generally 2 or 4 bytes of data are involved. You work with 16-bit data or work with 32-bit data. You cannot generally transfer 8-bit data, but there are certain exceptions. We'll come to that. Now, whenever a 16-bit data is transferred onto the stack, we call it as a push operation. When you store something on the stack, it is push. When you read something from the stack or retrieve something from the stack, it is called as a pop operation. So whenever you store something onto the stack, that is a 16-bit data, the MSB will be stored in SP-1, that is stack pointer -1, whatever is the value that is pointed towards by the stack pointer, -1. In that location the MSB will be stored, and in the next location the LSB will be stored. And generally the contents of the stack pointer register are decremented by 2. Now, as far as the stack is concerned, stack is going to be a special area in memory, and you would be making use of a combination of the stack segment register along with the stack pointer. In some cases you might use the base pointer, but mainly it is a combination of the stack segment register and the stack pointer that you will be using. So now we are not using the data segment register. We are using the stack segment, and along with the stack segment, the offset is going to be present in the stack pointer. So let's have a look at the first operation, because you have to store something before you retrieve it. So let's have a look at the push operation. It is possible for you to push data It's possible for you to push data from the registers or the segment register. It is possible for you to store data from memory onto the stack. It is possible for you to store data from the flag register onto the stack. So you can transfer data from registers or segment registers to the stack, from memory to the stack, or from flag register to the stack. These are some examples of push instruction. Push AX will transfer the contents of the AX register onto the stack. Push EBX transfers the contents of the EBX, which is a 32-bit register, onto the stack. Now, before any push operation is done, the stack pointer will be decremented. If it is going to be push AX, the stack pointer is decremented by 2, and then the contents of AX is transferred onto the stack. When you say push EBX, stack pointer is decremented by 4, then the content of EBX is transferred onto the stack. Push DS transfers the data segment, but before that the stack pointer will be decremented by 2. You can push the contents of memory. Word pointer BX means that BX is pointing towards a 16-bit data in memory. You can push the flag onto the stack. You can push the E flag onto the stack. Whenever you're using the suffix D, it means that you're working with a double word. So you can transfer the E flag, which is available in 386 or 486, onto the stack. So push FD works only with the 386 registers. There are other instructions for push also. Push A transfers the contents of all the registers onto the stack. AX, BX, CX, DX, registers onto the stack, that is push A. And push AD transfers all the 32-bit general purpose registers onto the stack. But the push A or the push AD instructions are not available in 8086. These instructions which I have indicated in red are available only from the 286 processor. And again, if it has to be push AD, it is 32-bit register, hence it's available only in 386. You can push a 8-bit data onto the stack, 8-bit immediate data onto the stack. You can push a 16-bit immediate data onto the stack, or you can push a 32-bit immediate data onto the stack. Again, push D would mean that you're working with 32-bit data. So if you're working with 32-bit data, your processor has to be a 32-bit processor. So these are some examples of push instruction. But then more than the examples of the instruction or the format of the instruction, we have to understand how the stack works. So let's see how the stack is going to work with the help of an example program. So in this program, I am pushing the contents of AX followed by BX followed by SI followed by a data in memory. I am using indirect addressing. Word pointer indicates that this address is pointing towards a 16-bit data, and that is followed by pushing the flag contents. So just remember that AX, BX, SI, the word pointer, and then the flag register. So let's look at how the stack memory is going to be organized. Now remember, I said that whenever we're talking about stack, we use a combination of the stack segment and the stack pointer. The stack segment has 7000 in it. The stack pointer has 050 in it. So the current stack address, if you look at it, would be a combination of the stack segment shifted left by 4 bits plus the stack pointer. So the address would be 7050 would be the address which is currently pointed towards in the stack. So it's a combination of stack pointer and the stack segment register. And another thing you can notice is my memory locations are arranged in a descending order as against generally the ascending order which we use for arranging this. So I'm starting from the location 70050. So the stack pointer would be pointing towards 0050. Now if I say push AX, the first thing that happens is the stack pointer gets decremented by 2. So the stack pointer now has a value 004E in it. Whatever is shown in brackets here is going to be the value that is present in the stack pointer. So push AX will first cause the stack pointer to be decremented by 2. So the current address then becomes 7004E. So this is going to be the new stack address. So into this, the content of the AX register would be transferred. How? 4F will be having the contents of AH and 4E will be having the contents of AL. Now am I violating the little endian rule? No. Because according to the little endian rule, the first memory location must have the lower byte and the next memory location must have the higher byte. The first memory location of course is 4E. So that has the lower byte and 4F is going to be having the higher byte. 4F has AH and 4E has AL. You have to remember now the stack pointer has a value 004E. Our next instruction was to push the contents of the BX register. So if it encounters the instruction push BX, what it will do is it will decrement the stack pointer by 2. When it decrements the stack pointer by 2, it now points towards 004C. The contents of BX register would be transferred into location 7004C. Because now the stack pointer has 004C, the address becomes 7004C. So how it will be stored? BH will have the contents of 4D and 4C will be having the contents of the BL register. The next instruction was to transfer the contents of the memory location into the stack. So the instruction was push memory location. I think the instruction was push word pointer and then BX was given. So here again the stack pointer, sorry, it was not push memory contents, it was push SI. So push SI would cause the stack pointer to be decremented by 2. So the stack pointer now would point towards location 004A, and the contents of the source index register would be transferred into location 7004A. Here again the source index higher byte would be in 4B, the lower byte would be in 4A. So now the stack pointer has a value 004A. The next instruction was actually pushing the contents of memory location onto the stack, and the memory location was given using register indirect. The register which was used was the BX register, and we had said push word pointer within bracket BX, the word pointer indicating that BX is pointing towards a 16-bit memory location. So procedure remains the same. Stack pointer is going to be decremented by 2, so it moves from 4A to 48, and the contents of memory will be transferred into 70048. Here again the higher byte being in 49, the lower byte being in 48. The next instruction was to transfer the contents of the flags onto the stack. That was push F. So push F, what will happen here again is the stack pointer now has 0048, gets decremented by 2 again. So the stack pointer content will become 0046 now, and the contents of the flags will be transferred to location 70046. So the value here is going to be stored in 70046. Here again the higher byte of the flag will be in 47, the lower byte of the flag will be in 46. So at the end of the operation the stack pointer will have a value 0046 in it. It started with 0050, now the value is 0046. So the current stack address would be 70046 is going to be the current stack address. So every time a push instruction is going to be executed, the stack pointer will be decremented by 2 if it's a 16-bit push operation. It will be decremented by 4 if it is a 32-bit push operation. And whatever is the current address, into that address the contents of register or memory is going to be stored. So this is how data is going to be transferred onto the stack. Now to get the data out of the stack, we have to make use of the other instruction, which is going to be the pop instruction. So let's see how the pop instruction is going to work. Pop is the reverse of push, or it's the inverse of push. It takes the data from the stack into register or memory. Data popped again can be 16 bits or it can be 32 bits. So you can do 2 bytes or you can do 4 bytes. The first byte from the stack will always move to the lower register if it is 16 bits. The second byte will move to the higher register. And after that, the stack pointer is going to be incremented by 2. Remember, in case of push, stack pointer was decremented by 2. Contents of register was transferred onto the stack. In case of pop, contents of stack is transferred to the register, then the stack pointer is incremented by 2. That's why it is exactly the inverse operation. So for example, I can say pop AX, which will retrieve the contents of the stack and transfer it into the AX register. I can say pop CX, which will retrieve the contents from the stack and transfer it into the CX register, after which the stack pointer is going to be incremented by 2. Pop word pointer into BX takes the contents of the stack pointer and then transfers it into a memory location. Again, stack pointer is incremented by 2. Now, let's see how the push-pop combination work together. Let's look at a series of memory locations starting from 46 to 4F. Now, the stack pointer will always point towards one location plus the last on the stack. This is going to be the set of stack locations which I am going to have. 0046 to 004F is going to be the stack locations which I am going to have. So my stack pointer is going to point towards always the last address of the stack plus 1. the last address of the stack is 004F. So it is pointing towards 0050. So stack pointer, last location's displacement plus 1. So the last location's displacement is 004F plus 1 is going to be 0050. So the stack pointer is pointing towards 0050. So my stack area starts from 46 and goes up to 4F. So let's see push and pop along with an example. So the first thing is, let's assume that the AX register has a value 3456, BX has 12AB, CX has 7FDC, and a combination of the stack segment and the stack pointer is going to have a value 7000050. So this is going to be the contents of stack segment and stack pointer together. These are the series of instructions that have to be executed one after the other. You can see that I have 3 push instructions: push AX, push BX, push CX, and then I have pop AX, pop BX, and pop CX. So let's see what is going to happen. So the stack pointer is pointing towards 70050. Now if I am going to execute the instruction push AX, the stack pointer will be decremented by 2. It will point towards 004E at this particular point of time, and the contents of AX register will be stored in 4E and 4F. 4E will have the data 56 and 4F will have the data 34. Now if it executes the instruction push BX, the stack pointer will be again decremented by 2. So it points towards the location 7004C. And this is push BX. So the contents of BX register is going to be transferred. So the BX register contents would be transferred in this manner: 7004C and 7004D. The lower byte AB will be present in 4C, and the upper byte or the higher byte would be present in 4D. So AB 12. This is the way it is going to be stored. The next instruction is going to be push CX. So if it is executing the next instruction, once again the stack pointer is going to be decremented by 2. Now the stack pointer is pointing towards the memory location, which is going to be 7004A. Now the contents of CX register is going to be transferred. Again, the lower byte would be in the first location, the higher byte in the next location. So it is going to be DC7F. So right now the stack pointer is pointing towards location 7004A. So the SP contents, if you are going to look at it, is going to be 004A. Of course, the stack segment is not going to be affected. It continues to have 700 in it. Now, the next instruction is going to be pop AX. So pop AX would mean that the contents of the stack will be transferred onto the AX register. Then the stack pointer is incremented by 2. So the contents of the stack, currently the stack pointer is pointing towards the data 7FDC. So if I say pop AX, the value 7FDC will be transferred into the AX register, and then the stack pointer will be incremented by 2. So now the stack pointer points towards 7004C. If I say pop BX, the value which is going to be 12AB will be transferred into the BX register, and then the stack pointer again incremented by 2. If I now say pop CX, the contents of stack pointer is pointing towards 7004E. So the content of this location, that is 3456, will be transferred into the CX register, and then the stack pointer will be incremented by 2. So stack pointer has come back to its original location, that is 0050. But what has happened? We have exchanged the contents of AX register and CX register. Remember, our policy was last in, first out. So what went in last was the CX register, and the contents of the CX register was popped into the AX register. If the plan was to retrieve back the content of AX, retrieve back the content of BX and retrieve back the contents of CX register, the order in which I should have popped should have been pop CX followed by pop BX, that was in the correct position, followed by pop AX. So this would have ensured that whatever was the original contents would have returned back into the registers. So if you are pushing in the order AX, BX, CX, the popping has to be in the order CX, BX, AX. That is why the term is last in, first out. So if the last data to go in was CX, you should have to pop back whatever was stored into the stack into the CX register. Otherwise, you might end up getting the wrong data. So this is how the stack is going to work. Stack is nothing special. It is part of the memory. The only thing is, instead of accessing it randomly, there is a policy that is going to be followed, that is last in, first out. And whenever you are accessing the stack, you have to remember that you will be making use of a combination of the stack segment register and the stack pointer. So I will stop with this in this session.